Hey everybody, welcome back. In this video, we're going to start talking about something called a margin of error for a means. And I wanted to just talk about it for a couple of minutes before we jump into these formulas and why you would even have a margin of error for a mean. It would be like this. If I said, what if we wanted to calculate the population mean for, let's say, the males in Mr. Ellis's 5th period Math 3 AFM class. Well, to do that, to calculate the mean, we would need to take every male, weigh them, and sum that up, divided by the number of males, and then we could calculate a mean. So we wouldn't have a margin of error. But let me pose a different scenario to you. Suppose we said, I would like to know the mean weight of, let's say, the male deer in the Croatan National Forest. That value does exist. There is a mean weight of male deer in the Croatan National Forest. But a person couldn't practically capture every male deer and weigh them to find this mean. So a person might say, well, okay, now there's one way we could go at this. We could go out and say capture 100 of them, or if you thought you could get 1,000 over a year's time, which would be, I'm sure, a pretty big challenge. But you would literally have to capture a sample. All right. Well, if you only capture a sample, there's going to be some problem between an actual mean and what you've sampled. They won't be exactly the same. So that's sort of how I would introduce this idea. Is that what we're talking about are samples of a population, and that the real mean lives out there somewhere, but we don't know exactly what it is. Now, we can get close to it, and some of those things depend on the sample size, of course, and how close you want to get, and they call that a percent of confidence. So let's take a look at this. This is 9.3, and what we're talking about here is calculating a margin of error for a mean. And instead of writing margin of error every time, I just wrote MOE. I hope that's okay with you. All right, so like I said, this has to do with a sample. And notice when we start looking at these variables here, this Z star is actually a value that lives in a table. All right, so it's no mystery, because in the problems you're going to get, they're going to tell you the percentage of confidence they want. Okay? And all of these are going to have to do with samples. Because if you really want to know a mean, you can find one if you know the whole population. In fact, I would suggest that that's a fairly rare thing that happens in statistics, in real studies. You just wouldn't know. If you wanted to know the mean weight of females in North Carolina over 50 years old, there's no way you're going to get everyone. You would have to establish a sample size and do some random sampling, and then you would have an approximation, and that's the best you could do. All right, so we start talking about the N is the sample size. That'll be stated in the problem. In the next video, we'll actually do one of these. All right, now S, they're using S here instead of sigma. In some formulas, you'll see sigma. I've looked around. And I think S is, I like it better because it's a sample standard deviation. All right, so this population was sampled. There was a standard deviation S. Z star lives in this table. And it's a fairly straightforward calculation, okay? So keep in mind, the only reason you have a margin of error for a mean is you're dealing with a population sample. You don't know the entire population, and therefore you don't know the mean. But you can get close to it and have a level of confidence that you're within so many units of the real mean, okay? So that was a short introduction to this, and we'll do a problem in the next video, and I'll see you then.